Hello and welcome to this fourth and final tutorial in the mini-series on functions at the higher level. And we've saved the hardest till last. The topic that we'll be looking at in this tutorial is inverse functions, which I think does require a little bit of thinking for everyone. I don't think this is a simple topic certainly when you first come upon it. Right, inverse functions. Well, I think a good way to start thinking about this is to go to the rather formal language of functions regarding sets. So let's imagine we have two sets, and these will be rather old friends to you by now. So there's set X and here's set Y, okay, capital X and capital Y, and a given element of this set we'll label by little x, and a given element of this set we'll label by little y. And we will have a function, a mapping that takes us from set X to set Y, and with stunning absence of originality, yes, we're going to call it little f. So y is the outcome of applying the function f to element x. Right, now here's the question that we have. Can we go back? Can we go back from this element to that element? It's like the return journey. Well, let's say that we can for now, and let's call that mapping a name, and the name we use is the name of the forward journey, and then we put a -1, and that stands for inverse. So f was the forward journey, the function that takes you from x to y, and then the return journey from y to x is f, and we call it f to the -1 or f -1, okay, which is the inverse function. So thinking of this just as a function, what we have then is that x, the element x, is the outcome of applying this inverse function, f to the -1 or f -1, to the element y. Okay? Now, in order to strictly define a function, we remember we had to say that for a given element in the domain of the function, there had to be a unique landing point in the codomain, or in the set that the function is mapping to. So in order for that to be true, it does actually place a restriction on often on the domain x. I don't want to get too hung up on that actually, and maybe looking at some examples will make this a bit clearer. But in the language of sort of set theory, you'd have to say that the function f was both one-to-one and onto in order for there to be an inverse. But for our purposes at this level of maths, and actually to be honest, as a physicist talking about maths, we don't tend to get that formal. We will see that sometimes we just have to place a restriction on the domain of x in order for these functions to form a pair in which one is the inverse of the other. Just another word on language. This set x is the domain of the function f, and the set y as the outcome of that is the range of the function. So in terms of this inverse function, actually the set y now becomes the domain of the inverse function, and the set x becomes the range of that inverse function going in the opposite direction. Right, now a very, very important outcome of these two statements here is the following, that indeed if x is the outcome of applying f -1 to y, and if we think of y as f of x, we can write this as a composite function. And do you see how the outcome of applying the inverse function to that function of which it is the inverse, so applying f minus 1 to f, gives you back the argument? All right. So let me perhaps write that in a sort of more symbolic way. Again, not to get too hung up on x here, but if I apply the inverse function to the forward function of some argument, and I'm going to call that argument apple, I get back that argument. It's like wrapping something and then unwrapping it, and you just get back the thing that you were originally wrapping. And because f is just a symbol representing some function, we actually have the same statement that the function f applied to its inverse of some argument gives that argument. Essentially, this statement is like saying that if I start here from y, take this inverse function to x, and then come forward with f, I get back y again. But I'm not using y, I'm just using our friendly old symbol apple to indicate the thing that the functions are operating on. So I operate on something with the inverse, and then I operate again as a composite function with the forward function. I again get back the original argument inside. So these make a lot of sense. Think of wrapping and then unwrapping as a way to understand those. They're very useful relationships, and we'll see these again actually later on when we talk about exponentials and logarithms actually, and it will be really helpful when we come to understand a logarithm as an inverse function to an exponential to use these identities that are true for any pair of functions and inverses. Right, okay, good. Now let's just have a different point of view. Let's think about inverse function in terms of graphs. So let me start with a rather simple example. So I'm going to just make up a function here and plot it on xy axes. So what shall I choose for my function? I think I'll have one that I've used before. Let's say we have rather a steep function. Actually, you know, I'm going to just choose something slightly different to what I thought I was going to choose. I'm going to just start very simple indeed. Let's imagine we have a very straightforward function. F of x equals 2x. And that gives us y. So y equals f of x, which is 2x, and that would be that's rather steep straight line there. Now let's just remember sort of what we're doing when we think of graphing a function. We're starting with the value x, and we're essentially going right up vertically, and this graph tells us then the outcome y. And in this case you see a value. Let's imagine that value that we just chose there was 2. That value has been mapped to the value 4 because this graph is a graph of 2x with doubling the input to get the output. So that's the forward function. Now let's imagine, let me choose a different color here. What would the inverse function be? Well, the inverse just takes you back. So the inverse is starting from 4, going to this line, and then coming back down here. And you see that the inverse function takes 4 to 2. And in fact, any value that we choose, it will halve the value. So the inverse function here, f minus 1, and to avoid confusion I'm just going to put apple, is to halve the value, apple divided by 2. So I hope this isn't too confusing now. What we can do on this graph is plot the function f minus 1 of x. okay, which is actually x over 2. And let's just plot that. Be quite a shallow function passing through the origin. All right. And what this function does, you see, it halves the input. So if I take x equal to 4, it gives me an output, which is y equals 2. Okay. I think this can be very confusing because I think everyone's fine up until the point I drew this other line, because yes, we can see that by going backwards we have a halving function. And actually there's an old trick of how do you see what the inverse function actually looks like. You can take your piece of paper, turn it over and tilt it and hold it up to the light, and you would see the line, a shallow straight line, which is the one I've actually drawn here. Drawing the same shallow line on the same graph can look a little bit confusing. The reason I'm doing it though is to show you something very interesting, which is actually this line is a reflection of the original function about the line y equals x, which I will draw as a dashed line. And in fact, you can use this mirror. Y equals x is a mirror. You can use that as a mirror to get the inverse function for any function that you graph, and it's very, very useful, in fact. So let me show you an example of that, which hopefully you'll find helpful. So let's have a good old friend as a function, which is a parabola. Okay. Let's see if I can do a good sketch of a parabola here. Not too bad. Actually, that's not too bad at all. So that's the function y equals f of x equals x squared. And now what I want to do is think, well, what's the inverse function and can I sketch it? And we want to reflect about this diagonal line y equals x. So there's that diagonal line. It's hard to sketch without tilting the paper. I'm just going to change where I'm sitting here if I can sketch this. So there's that diagonal line y equals x. Think of that as the mirror. And I just want to reflect this blue curve about that mirror. Quite interesting this. Look, this point here is on the mirror, so by reflecting it just stays on the mirror. This point is on the mirror, so by reflecting that it stays on the mirror. This beautiful bow here would just be reflected in the mirror like that. And then this part going up would look like this, and then this whole branch here would look like that. And you see how we've reflected about the mirror. This parabola sort of looks like a parabola in this direction, which is exactly actually what it is. That red line is the function y equals the square root of x. More formally, it is the inverse function of x, where the inverse of the function x squared. Now we have to be a little bit careful here, which is that plotting this as a function is not really, strictly speaking, a function, you see, because it's multi-valued. So really, as we had this exact function a couple of tutorials ago, we would really only plot this one and maybe have this as a dashed line, and we would call that, say, the negative branch of root x and that the positive branch of root x. But just to put some numbers on here, this would be the value 0. The value of x which wasn't affected by the reflection is just the value 1, because 1 squared is 1 and the square root of 1 is 1. Okay. And yeah, it's probably a bit hard to draw other values on here at the moment. just because I don't have enough room. Let's just be a bit formal and use this language here to derive what the inverse function of x squared is, even though it's sort of obvious. For example, the value 2 would map to 4, but I don't have room on this graph really to draw that. Going back from 4 to 2 seems clear that that is a square root. But how would we actually show that? So let's be quite formal here, and let's say that we have a function f of x equals x squared. And we want to know what the inverse function is. A very formal way of doing that is to say, right, well, we know that whatever that inverse function is, if I take f of that inverse function, I will just get back x. Okay? And thinking of f of apple as apple squared, because that's really what this is telling us, and you can see how it's so easy to get confused with all these x's everywhere. Just forget about x. It's just the default input or argument of a function. Think of that definition as f of apple is apple squared. We know, strictly speaking, that f of its inverse of an argument gives us back the argument. Then we know now, okay, what's effectively the apple is the inverse function. So f of apple is apple squared. So we have that the inverse function, all squared, because that's the operation of f on that, is just equal to x. And then I can just take the square root to reveal this object here. Taking the square root of each side gives me f minus 1 of x is the square root of x. And that is deriving for us the form of the inverse function. So let me just recap briefly here this graph aspect of this topic, and then we'll just end with a couple more examples. So thinking about inverse functions on graphs, there's sort of two aspects to it really. One is thinking of starting with a value of x. The function takes you to a value of y, and then the inverse function is something which takes you back along that path. And as I say, there's this old trick of seeing, well, what would that function look like? Well, you take your piece of paper, you turn it over and rotate it at the same time. If you hold it up to the light, you'll see a picture of what that function looks like. If you actually just want to draw that function without doing that sort of turning over the paper business, sort of lightly sketch the line y equals x and use that as a mirror, and then reflect your original function about that mirror, and that will give you then a graph of the inverse function, and what you're plotting is literally f minus 1 of x. To derive the form of that inverse function, we've done quite a formal thing here, and taken our original function, and we've said we're going to use these identities, that the f of its inverse gives you just back the argument, and in this particular example, f of its argument, f of apple, was just apple squared. So f of this argument, which is the inverse function, is x. And in this case then, the inverse function, all squared, is x. And we thereby can take the square root in this case and get an expression for our inverse function. So let me do a couple more examples to end the tutorial here. Let's imagine something very straightforward to start with. Let's imagine we have f of x equals, let's say we have 1 take away 3x. And the question we're asked is, what's the inverse function? And we would normally express that as a function of x, because that's kind of what we always do, is express functions in terms of x, if we have no other good reason to have a different named symbol. Let's do this the formal way, but then I want to show you a trick, which is for some people a much easier way to think about this. But the formal way is, right, in the back of our minds, we're thinking f of apple is 1 minus 3 apple. And then the formal statement is, well, f applied to the inverse function gives me back the argument of that inverse function, x. F, though, just is an operator that takes something and turns it into 1 minus 3 times that thing. So here then I would have 1 take away 3 lots of the argument of f, which is f minus 1, and that has to equal x. And now I just solve this equation for f minus 1. So let's see. Let's just do this in a few steps here, because I know some folks are a bit nervous with manipulating equations. So let's just do it in a couple of steps. I could take this over here and take the x over here. So taking x to the left-hand side and taking negative 3f minus 1 to the right-hand side, I would have this. And then I can just divide by 3 on both sides to get f minus 1. And so I would get that f minus 1 of x is 1 minus x divided by 3. So that's a sort of a formal derivation of the inverse function of f. Now, a sort of a trick method, or I say trick, a method which is sort of meant to be quite helpful. I think for some folks it will be very helpful. For others they might find it very confusing. I don't know. Let me just show it to you because you might find it helpful. So let me call this a helpful alternative. Personally, I sort of like this method, but you might find this a helpful alternative. Is the following. If you're given a function, write it as y equals the f of x, which is 1 minus 3x in this case. And then, this could be quite confusing, switch x and y, exclamation mark. So let's just do that. So wherever we see y, we write x, and wherever we see x, we write y. And then solve for y. Solve for y. Sorry, my handwriting is particularly opaque. I apologize. So we're going to solve this equation for y. Now you see, actually, we just have the same equation that we were solving here. So I won't go into any details here. We can take minus 3y over here, x over there, divide by 3, and we would find y equals 1 take away x divided by 3. And then the final step, I guess, is that you just label that y as your inverse function of x. So it's essentially equivalent. I think it lacks a certain sort of formality, and it might be that you use this without really understanding why it's correct. What's nice about this method is you are using an identity that defines an inverse function, and you're really just solving that identity to get your inverse. So it's a very formal, comprehensible way of doing the problem. This is more of possibly a trick or a sort of a crutch for those who don't like this very formal method and just want some kind of simple way to get through the question. Right, let's just do one more example, something a bit crazier maybe. Let's say our function f of x is to take away the sine of the square root of x. That's quite an unusual function, and we have to find the inverse function to that. I'm going to use the formal way to do this, and maybe it'd be a good exercise if you wish to repeat that using this kind of trick method. Right, I'm first of all going to sort of remind myself that what this really means is that f of apple is to take away the sine of the square root of apple, because it's such a messy function. I don't want x hanging around, because I want to use x in the next line, which is to write this identity down. So I'm going to write that f of its inverse is equal to the argument of that inverse, which is x. And now, because I've got this sort of funny f of apple expression, it's very easy for me to say, okay, f of this object literally means to take away the sine of the square root of that object, which is f minus 1, and that is equal to x. I'm just writing f minus 1 for short now because it's a bit messy here, but it is of x, okay? Right, I have to solve this rather amusing equation, so I'm going to take the sine function to the right-hand side, I'm going to take x to the left-hand side, so I would get 2 take away x equals sine of the square root of f minus 1. I'm going to need a bit more space here. And then I'm going to take the inverse sine of both sides. And maybe we'll talk more about this when we do trigonometry at the higher level. You'll have met the inverse sine function many times before, but maybe you've never quite appreciated it as an inverse function until now. Because when I take the inverse sine of 2 minus x, applying the inverse sine to sine literally will give me the argument, because it is literally the inverse function of sine. So this will just give me the argument of sine, which is the square root of f minus 1. And finally, I'm going to square both sides. This is a really horrible example I'm ending with, so if this looks horrible, don't worry. I don't think you would be set problems this hideous at this level of maths, but it's just to show you that using the technique and the algorithm that we've talked about can pretty much deal with any situation, even one as rather desperate as this. So we wanted to get rid of that sine, so we applied the inverse sine. We want to get rid of this square root, so we're going to square both sides. So ironically, in order to solve our inverse function problem, we're actually applying quite naturally lots of well-known inverse functions like square and square root, sine and inverse sine, to uncover f minus 1. So squaring both sides, then I have that the square of sine to the minus 1 of 2 minus x equals the square of the right-hand side, which is just what I wanted, f minus 1 of x. And that is the solution. Okay. Quite a daft thing to end on, but you know, maybe that was okay for you. Maybe that was actually quite, enjoyable to see how one could solve that. That is inverse functions, thinking about them in terms of the set theory way of defining functions with a mapping in the opposite direction from y to x. This is very nice because you see from here these very, very useful formal expressions for the inverse function applied to the original function gives you back the argument, or the function applied to its inverse gives you back the argument. Really useful when you're thinking about functions and inverses, perhaps in unfamiliar settings, and we're really going to make great use of these when we talk about exponentials and logarithms. Thinking about what does it mean to have inverse functions with a graph, and I'm not going to re-explain these because I'll probably do more harm than good. Just to say though that drawing this mirror of y equals x is a very useful way to quickly sketch what the inverse of a function would look like as that inverse function as a function of x. And then we just did a few examples using this formal method to find the inverse of a function that one may be given and expressing that inverse as a function of x. Did a really complicated example here, and then I quickly showed you sort of more of a kind of an alternative way to think about it if you really don't like the formal stuff, which is really more of a trick, I would say, writing your function as y equals f of x, switching x and y, and then solving for y is kind of a fail-safe way to get that inverse function of x. Right, good. So we are done with the topic of functions per se. I hope it's been useful. I'm going to do one quick tutorial on sort of drawing graphs, but it's really kind of part of the functions topic. It's thinking about drawing graphs where one's changing arguments or aspects of a function. And then, as I mentioned at the end of the last tutorial, then we get to have great fun doing the topic of calculus. Great. Hope that's helpful, and I'll see you next time.